When we were talking about the Newton form in the previous recording, I was telling you how great it is that you don't have to solve a system of equations because the whole thing is diagonalized. Well, guess what? It gets even better at this point because we can actually avoid solving any equations whatsoever. We can get our results immediately. And to demonstrate how this actually works, I want to talk about divided differences. Now, it's a more complicated concept in terms of derivation, so please bear with me as I explain how the whole thing goes. Now, remember we had a set of formulae for the overall polynomial, and we can sort of subdivide it into the particular parts which are relevant for the solution, i.e. the value of the function. So for example, if we're considering let's say linear polynomials, linear interpolation to begin with, then we could have the following definition. We could have f0 being defined as a0, like we had in the previous example. Remember, we got the a0 pretty instantly, and then we have f1 being equal to a0 plus x1 minus x0 multiplied by a1. So that's what we had before. We also had f2, f3, f4, I think. No, actually we had just f2 and f3, but we're going to keep it simple for now, because what we're going to do now is we're going to subtract one from the other. We're going to subtract f0 from f1. And what we'll get is the following. We'll get f1 minus f0 equals x1 minus x0 multiplied by a1. The a0's go when you subtract. So now we can take f1 minus f0, we can divide them by x1 minus x0, and we get the following. We get a1 equals f1 minus f0 divided by x1 minus x0. And so we're going to introduce another form of notation, because this thing that we've just come up with is what's called a first divided difference of the function f. So let's write this down. This is a first divided difference. And we're going to introduce a notation where the f is going to have square brackets, and we'll have the terms in there. So here it's x0 and x1, so we can write them down like so, x0 and x1. And as you can imagine, if you were to swap x0 and x1, you will get exactly the same result, because you'll simply get a minus here and minus here, and that will cancel out whatever the signs are. So we can say that the divided difference, the first, in fact, divided difference between x0 and x1 is the same as the divided difference between x1 and x0. So this divided difference may appear as an artificial construct, a kind of, something that we've just invented, but we're going to stick with it, because now that we've done the linear case, this was the linear case, we're going to add another term. We're going to add the f2 term here and consider the quadratic case. Quadratic. Okay, so the quadratic case would look something like the following. We'll introduce the term f2, and f2 is going to be a0 plus x2 minus x0 plus x2 minus x0, x2 minus x1 multiplied by a2. And I think I forgot an a1 here as well. Okay, so what can we do with this? Well, we can do f2 minus the f1 that we had before. We can take this and subtract from this. So we'll say f2 minus f1. Okay, so this could be tricky. Some terms will actually cancel out. Let's take a look at those terms which will cancel out. So f2 minus f1, the a0's, they cancel out. And also minus x0 times a1 here and minus x0 times a1 here. These things will cancel out, but everything else will remain. So what we'll end up with is the following. We'll end up with x2 minus x1. The x2 comes from here, and the x1 comes from here. So x2 minus x1 times a1 plus x2 minus x0, x2 minus x1 multiplied by a2. Okay, so now what we can see from this is we can see that these terms are identical, x2 minus x1. So we may as well divide by them effectively. So we have f2 minus f1 divided by x2 minus x1, and that's being defined as the following. So it's the divided difference. Now, the divided difference, where does it come from? Well, it comes from a1, because remember, a1 is the first divided difference. That's what we came up with as our notation. So f2 minus f1 divided by x2 minus x1 is the first divided difference between x0 and x1 plus x2 minus x0, that's this term times a2. Okay, so now we introduce yet another term, or we're almost ready to introduce yet another term, because we want to extract the a2. So how do we extract a2? Well, we once again rearrange the entire thing. So we essentially have this notation that this particular construct, being the first divided difference between 1 and 2, we'll rewrite this as f with square brackets x1, x2. Okay, and what we do to get the a1 is we take this part. So we take this part, we move it over to this side, and then we divide by x2 minus x0. So a2 is now defined as follows. It's defined as divided difference between x0, x1 minus divided difference. Actually, that should be a1 and a2 here. So the x1, x2 minus this part, so divided difference between x0 and x1, all divided by x2 minus x1. Okay, and once again, we're going to introduce a notation for this divided difference. The notation will be that we'll now have f with square brackets, and we'll have all the three terms. So x0, x1, and x2. x0, x1, x2. And this is going to be the second divided difference. Second divided difference. Okay, right, now we can continue this onwards, and we can actually come up with the third divided difference, but we're going to employ a bit of a trick to actually come up with the last one. Now remember that when we're interpolating the polynomial, it really doesn't matter what the order of the points are, because we can shuffle the points around, and because we have this assumption, and I haven't given a proof to this, but I've alluded to the fact that the interpolating polynomial is a unique polynomial, we are in fact to rearrange the position of x0, x1, x2, x3 as we want when we're interpolating it. So for example, for describing a3, which is the next thing that we want, I want to rearrange the points a little bit, so we'll have the points in the following order. We'll have the points as x2, x1, x0, and then x3. And this is a trick that I'm doing because now what I want to do, if you remember in the previous clip, we actually had a third order polynomial, and that's exactly what I want to do. I want to take these points and plug them into the third order polynomial, the p3 of x. And we had this before, but now the order has changed. So essentially the first point here will not be a of 0, it will be a of 2, which we know is f of 2 by definition. So in here we have f2 plus, and then here we have the x1, so that's going to be x minus x2 multiplied by the first divided difference between x1 and x2 plus then x minus x2, x minus x1 multiplied by the second divided difference, so x0, x1, x2, and then plus we should be having a third divided difference, but we haven't come up with it yet, so we need to formulate it. And for the time being, we're going to stick with this a notation. So remember, like before we had the a2 before we gave it some expression in terms of the divided difference. Well, guess what? At the moment, we don't have an expression for the third divided difference, so I'm just going to write out the terms here. So we'll have x minus x0 multiplied by x minus x1 multiplied by x minus x2 multiplied by a3. And we're obviously interested in a3, and we're going to adopt the same process that we had before in order to figure out what it actually equals. So we're interpolating at a point x3, and we're essentially expressing f3 in terms of, well, all of this really, and we have to do something about it. But what can we do? What can we divide by? Well, we can first of all divide by x3 minus x2. Well, actually, I'm going to do something different first of all. So I'll take the f2 that we have here. I'll take the f2, I'll move it to the other side. So we'll have f3 essentially minus f2. And that's going to be lots of stuff. And then we're going to divide everything that's in here. So we're going to divide it by, we take the f3, so we take the third point. So when we talk about x, we're really plugging in x3 everywhere. So that's, you know, becoming x3 in all locations. And this is what's actually going to let us simplify this whole thing, because we're going to divide by x3 minus x2. Let me underline those points where this is actually present. So we're going to divide the whole thing on both sides by x3 minus x2. And what we get on the right is the following. We get the first divided difference between x1 and x2 plus x3 minus x1 multiplied by the second divided difference, x0, x1, x2, and plus x3 minus x0, x3 minus x1 times a3. So now you should probably recognize this part already, because this is the divided difference between 3 and 2. So we can rewrite this as the first divided difference, x2, x3. Okay, so we can continue simplifying this, because remember, eventually we want to come up with a3 somehow. So let's continue this arduous journey in attempting to simplify the whole thing. So essentially, first of all, I'm going to once again take this term and move it over to the other side. So we'll have the fx2, x3 minus fx1, x2, and all we're left with is this bit, this whole bit. And we want to get a3 from it somehow. And you'll notice that once again we have a common term that we want to divide by, and that's x3 minus x1. So if we rearrange the entire thing, we get something like the following. So we get x3 minus x0, a3 on the left. I'm just going to swap these things around. So we'll have x3 minus x0 multiplied by a3. And on the right-hand side, we have the following. So remember, we divided everything by x3 minus x0. Actually, x1 it should be. And here we have a divided difference between x2, x3 minus divided difference between x1, x2 minus the second divided difference, x1, x2, x3. There we go. So we're almost there. We're almost at an expression for A3. Because essentially, if you look up at this part, you can see that this particular thing, this entire construct, this thing, is the definition of the second divided difference. So I can effectively rewrite this as a second divided difference, x1, x2, x3, minus the second divided difference, x1. Well, actually, no. That should be x0 here. So I think I copied them over incorrectly. x0, x1, and x2, and that would be x0, x1, and x2. And so we divide by x3 minus x0, so we can cross it over and put it here, x3 minus x0, and guess what? This is A3, and it happens to be the third divided difference. And it might not be obvious to you as to why this is so great, but in actual fact, if you look at each pair of the divided differences, you'll see that instead of solving any equations, all we have to do is plug in the values from the previous divided difference to get the next divided difference. So it's kind of like a triangle that folds on itself. So first of all, you have just the f values, and then you have the first divided differences, which fall to the second divided differences, and so on and so forth. And in the next clip, we'll actually take a look at some examples.